Greetings, welcome. I'm in one of those phases right now where there's like 27 things I want to work on all at the same time, but I usually end up just basically like a dog chasing its tail when I try to do that. But I want to return to the pulse motor, and there's a lot more I know about it. Let's skip all that and stick focused. So what was I saying? That we talked about skin effect and proximity effect. Now we want to talk about Wheeler's formulas for induction. So to give the lay of the land here, bringing it back to Q factor. Q factor, as far as I can tell, and from the equations that I've seen as well, is pretty much defined by your pulse duration over the tau time of the coil. So the tau time is how quickly the coil will charge to 63% of its maximum field strength. So just as you have like a RC constant curve for charging a capacitor from a constant voltage source where it charges up quickly and then more slowly until after about 5 tau times of the capacitor you have a fully charged capacitor. The same thing happens with the magnetic field of the coil. So you have the tau time, which will be a number of milliseconds or microseconds. Then you have your pulse duration. And the shorter the pulse duration is as a ratio over that tau time, the better your Q factor. So you think, well, it's real easy then. You just go with a shorter and shorter pulse. But as we talked about in the last video, when you go with shorter and shorter pulse, you start running into reactive resistance caused by skin and or proximity effect. Now, what's the tau time defined as? The tau time is defined as the induction of your inductor over the straight line DC resistance, unless that straight line DC resistance now becomes straight line DC resistance plus reactive resistance. So when you start running into the skin effect and the proximity effect, the tau time of your coil begins to become shorter and shorter. We just said that you want the lowest ratio of the pulse time over the tau time. So if your tau time becomes half as short, your pulse duration is the same, the Q factor gets worse. So you don't want the impedance, the straight line DC resistance plus reactive resistance of your coil to be increasing because of proximity and skin effects. And so we talked a bit in the last video about how you mitigate those. And for instance, for proximity, you make the two wires less proximate to each other. And kaboom. And now you've gotten rid of most to all of proximity effect. For skin effect, you can use thinner gauge wire, although that brings up issues of the resistance of the wire, or you could use twisted Litz wire. Skin effect usually becomes an issue much later on than proximity effect. Proximity effect's a big one. So you want to space out the wire. Now, that brings up another engineering constraint. Suppose you move the wires apart in your coil, you're going to get less induction than if they were all bunched in right tight next to each other. Recall tau time, induction over resistance. So now your induction's going down, which means that your tau time is getting shorter, which means Q is getting worse. It doesn't have to be that you don't ever get anywhere. So in other words, there are kind of two scenarios you could think of. You re-engineer the coil, say to get rid of proximity effect, such that you don't run into increased resistance from skin or proximity effect until you're going at twice as fast. So a pulse duration half as long. Half as long means better ratio. But you've lost fourfold induction. Then the Q factor will be twice as bad. But what if you only lose 20% and you can go 8 times as fast? And it's like, well, yeah, now you can really continue to improve a long time with the Q factor. And that's sort of what you can do. Maybe not quite that good, but you can do things along those lines. But in order to have a clear idea of how to approach that, you want to know what's going to happen to the induction. Say if I double the space between the wires, or if instead of using a multi-layer coil, I use a single layer coil, or I use a pancake coil. How is the induction going to behave? And then for each of those, you want to think about, and this is even, not even considering if you're putting in some sort of core of ferrite or whatever material you're using for the core, what sort of air gap do you want for a pancake coil? What should be the length versus the width of a multi-layer coil to get the most induction for a given length of wire? That's sort of what you're looking for there, because whenever you add wire without getting more induction, you're increasing resistance, and you're not increasing induction. So the tau time is becoming shorter, Q factor is getting worse. So you want to know, what shape in general should the coil be, and then if I start making changes, what can I do? I mean, you don't want like one wire and then a 3-inch space and then a second wire. What can I do to mitigate proximity effect and still preserve as much of the induction as I can, as possible? So this brings us to Harold Wheeler, and this scientist in, I want to say the 1960s, it might have been the 40s, 60s, we'll know in a moment, we'll look it up and talk about it. But he, at the National Bureau of Standards, I think it was called that, now it's called National Institute of Standards, maybe I got those reversed, but he basically just wound coils different ways and measured the induction, and then he forced equations to fit that. This wasn't like any, okay, I have an insight exactly of what's going on. It was all empirical and then back engineered equations. And the equations they approximate. If you start making really goofy coils, and I noticed this myself, the equations break down. But for kind of your standard coils of different kinds, multi-layer, pancake coil, single layer, a big strip of wire, they fit pretty darn well. And we're not even going to talk, then you get into like the really weird, like Mobius strip coil or something like that. We're not even going to worry about any of that. And maybe someday I'll get a chance to look at that and what might be going on with some of the weirder ideas. So what we'll do is we'll talk a little bit about Harold Wheeler. We'll look at what his actual equations are for the different kinds of ways you might set up a coil. And then, where it actually becomes useful is there's calculators all over the internet where you just plug in the values and you see what happens to the induction. So you can say, all right, well, what if I space the wires 1 wire length apart, 2 wire lengths apart? What's going to happen to the induction? And what if I have a giant air core? What if I have a small air core? What if it's twice as long as it is wide, or twice as wide as it is long? And you can kind of have an idea of what you're going to end up with before you wind it, which is nice. So let's get to the actual material now. And away we go. So here's Harold Wheeler, and we won't spend a lot of time on this, but they have a nice little tribute at the National Academy of Engineering for him, and I think suffice it to say he was a real smart guy. He did a lot of stuff. He did a lot of stuff with antennas and in a lot of other areas. He invented the Nutridyne. Anyone who invents the Nutridyne is pretty smart. And that was like, you know, I guess a huge thing for radio broadcasting for decades, before it became obsolete. And then really in his part-time he developed these equations, which are still the ones used today. Well, just real quick, so I mean, he worked also for the military for a lot and developed a lot of stuff for them. And here he built the world's largest antenna. Dozen fan like arrays covering an area of 2 square miles, 26 towers, each 1,000 feet tall. So he liked antennas. And this was phased array antennas. So as I said, smart guy. It doesn't say it here. Where did I see it? Here it is. During his education, he was working part-time at the National Bureau of Standards, and that's where he came up with all these equations that everyone uses still to this day. So if we go now to this site called Coil 64, Coil 32, there's a lot of good information here. I get the impression that these people know probably a lot more than me. They seem pretty bright. And here in the theory, they're just giving all of the formulas that Wheeler came up with for all of these different things. So for a straight conductor, it's that. Parallel conductor with the current flowing in the same direction, the current flowing in opposite directions, if you have a strip of wire, if you have a coaxial coil. Now here's the ones where it gets interesting for me. Single layer coil, looks like that. Multi-layer coil, flat or pancake coil. And even if you want to do a conical, you can get the formulas for that. So it's neat that there's all these formulas, and just real quick, you have your induction over here, and pi usually comes into play at some point. The U0 is the number for the magnetic permeability of air. So if you have a actual core of like ferrite or something, then that you got to add in what the relative permeability is of the material as well. N is your number of turns, R is your radius, L is your length. And so that's what you have here. And here you see the same things. N squared, turn squared. That's all the time there. R squared, radius squared. There's your pi again, and then you're worried about your radius, your length, and your width. And here with the flat spiral, n squared, r squared, u0, 8r, and 11w. So it's academically interesting that we have these, but I don't feel like plugging them all into a spreadsheet and trying to make sure I got it all right. So online calculators. Woo. Single layer coil calculator, multi-layer, multi-air ferrite toroid. So they, even if you want have a toroid, you can put that in there. Ferrite rod, flat spiral pancake Tesla coil, LC resonance calculator. We know how to do that. Reactance coil calculator. I haven't looked at that one. Some of these I haven't looked at. Some of them I don't know what they mean. Helical resonator bandpass filter. I'm not an engineer. I just like to have fun with electronics. So that sounds really cool, whatever it is. And so on and so forth. So the three that we're interested in is single layer, multi-layer, flat, pancake, Tesla coil. Let's start with this one. Now there's a tremendous amount I like about all these calculators that they've posted for us here, but there's one nit that I have to pick, is that I want to be able to put in number of turns, diameter, things like that, and get out the induction. What they want you to do is put in the induction, and then it'll tell you what these are. And so with a lot of other calculators, we'll look at one in a moment. You can do the opposite here. You can put these things in and get this stuff. But let's just go with what they have here first. So calculate So if you wanted 100 UH of induction and the inner diameter there was 10 millimeters, 1 millimeter wire diameter, this is kind of cool that you can check, well, 20 gauge. Now 20 gauge would be 8.12. What about if it was 15 gauge? Well, and they put it in automatically for you. So that's really nice. Let's go back to 1. Gap between turns. So here is like if you are gapping, just like they have here, with a width equal to the wire diameter. So here's, all right, here's the first thing. Yeah, I mean, I hope I'm not boring people, but this is really sort of the brass tacks of it is, you know, can you get rid of proximity and skin effect where you're still going to have enough induction left to improve Q? So let's say you got rid of this gap between the turns. I'm pointing at it with my finger for no reason. If you got rid of that gap, made it 0, oh, it probably wants something, 0, 0, 1. Now, okay, I don't care about the number of turns. What I care about is the length of wire, because the length of wire will tell you your resistance. So I didn't look at what that was before. 14 to 11. So in other words, if you space those things out, you're not going to get a lot more resistance. Or conversely, you're not going to lose that much induction if you kept it at, you know, you're not going to lose that much induction, and or you're not going to add that much resistance by spacing it out. It makes things worse, but it doesn't make them dramatically worse. And if you spaced it out where you have an extra wire length there, you could go, I believe, this is a little bit of a guess, but I believe you could go about 4 times as fast before you would run into proximity effect, as opposed to if they were right on top of each other. So, and again, this thing is kind of set up backwards from how I'd like it. But, you know, another question would be, well, do you want, you know, it'd be nice if you could make this air core really big here in the middle, because then you don't have to spend all your time winding. So here, let's keep everything else the same. We see that it's 14 meters. So if we also wanted 100 UH, what if we made the inner core, air core, 10 times as big? What's going to happen? Ooh, look at that. That's better, because now you only need 12 meters instead of 14 meters of wire to get the same induction, and you get a double bonus that you don't have to sit there winding all those, because a lot of it's your air core now. Now, take that to the extreme. Let's go with 1,000. Now you need 20. So let's go with what we were at. Okay, let's look at all of them again. 10, you needed 14 meters of wire for 100 UH. 100, you only needed 12. What about 200? 13. What about 50? 13. That's interesting. So right around 100 is where you would want that. And you can figure out, you know how much wire you got and things like that. And so how many winds. So you can kind of figure out how you want to set the thing up. And as I said, in this case, it would be nice to make this a 10 centimeter instead of 1 centimeter air core, so you save yourself from having to do those winds. Before we leave here, they credit that this is the equation that they're using from Harold Wheeler for this. Now let's go for the single layer coil. Let's go to the Excellent Electronics Tutorials website. because now we've got what I want, where you just put in the number of turns and you get the induction. Okay, my 3D print is done, so there should be a little less background noise. Let's just spend a couple minutes having a little bit of fun with this calculator, which is a single layer coil induction calculator. And again, they give the loop diameter, so how big you'd want the air core there. And the wire diameter, here's what we have with this setup. Let's add 100 turns. So now we're rid of the exponent there. There's a couple things that are interesting here. This one I thought was kind of interesting, where let's suppose first you double the loop diameter and you leave it 100 turns. So circumference is pi times diameter. So you'll have twice the length of wire. You'll have twice the resistance. This is 299, so you could almost call it 0003. Now, if we make this 40, it doesn't go up to 6 or just under 6. It goes up more than that. So that's actually good, that you would be increasing your induction faster than you're increasing resistance. Now, this is one I'm still working on wrapping my head around. But here's another thing that flows from these equations, and let's make this first just one giant farging loop. So we're going to have one turn, 2,000 inches, and you also notice the wire diameter has a small effect. See, as the diameter went down, the induction went up. So we're at 0.000348 henries. 0.00348. Now, if we made the loop diameter 1,000 inches, of course it goes down, but that's half the wire. So you'd have room on this, I got to stop pointing with my finger, on this coil now for 2 winds. 0.00348. The induction had doubled. Now let's go 504. 504. The induction has doubled. Now let's go 50 and 40. See, the induction, this is the same length of wire, and the induction is like an order of magnitude greater. 5 and 400. 0.5 and 4,000. And this all stems because when we looked at all of those formulas, the induction, it was always R squared, N squared, number of turns squared, that was affecting induction. So that's why, even though it's not good that the diameter is getting smaller, it's more than compensated for with the given length of wire by adding more turns. So let's just go, let's see if it'll do this one. 0.05, it might bark at us. No, it didn't. So you see, I mean, we were at 0.00347, now we're at 0.407, the same length of wire, 1,000 times more induction. And again, you know, with this Q game that we're playing here, induction over resistance gives you your tau time. Bigger the tau time, the longer the tau time, the better. And here you've increased induction near 1,000-fold, or I guess like 100-fold or 1,000-fold, somewhere around that. And resistance has been constant. Now, one thing is I diddled around with this. I actually took some 26 gauge and wrapped it around 18 gauge wire. It didn't give what Harold Wheeler, with his equations, was saying it would give. And if you go in depth on Wheeler's equations, they mention that the equations fall down in certain instances, and like where the length is much greater than the width or whatnot. So the further you get away from something like that, I mean, I just basically, you know, wound wire around like 5 feet of other wire, and it stunk. But what you can figure out, and this is going to be the topic of another video, is let's go back. If we go 0.5 would be, that would be 0.5, that would be 5, that would be 50. Just take a length of wire and, I don't know, have like a 4-inch core or a 2-inch core, 1-inch, half-inch, quarter-inch. I suspect it's around a 1/4 inch that you're no longer going to get improvement. But if things improve all the way down to like a 1/4 inch, this is what I was getting at about a radiator coil. Because, all right, you have a 1/4 inch, you want to put a bunch of turns on it, the thing's going to be 10 feet tall. It's not going to fit in the room. But you could have, you know, 6 inches, 2 inches over, 6 inches, 2 inches over, 6 inches, 2 inches over. They'd be far enough apart they wouldn't interact with each other, and you'd get a heck of a lot of induction without resistance. And that would be a really interesting way to try to get a high Q factor coil that I haven't seen done before. I imagine someone's done it, but I haven't seen it. And then, you know, maybe like turn it into a jewel thief or something like that. But to wrap this up and kind of bottom line it, we want to get rid of the proximity effect. If you have a multi-layer coil, where is it? Let's see. A multi-layer coil, you could do that, but you would want to space this layer from that layer, so each layer spaced apart, and then each winding spaced apart. And even with the 3D printer, it's a little bit of a bear to figure out how you would easily do that without making the wind an ordeal. So that leaves you two if you want to avoid that. And that is one that I'm going to try to look at. Maybe not, well, I've got some ideas on that. I'll just leave it at that. I think there's a fairly decent way. I mean, you could just like put some cardboard between each of these, and we'll get to the other part in a second here. But you either want to go to a single layer or a pancake coil. And that makes it easier if you want to space the windings apart. Now, one thing that I don't know, and that I started to look into, and then I saw some stuff that was interesting enough, I've gotten sidelined on it. Or not sidelined, but you know, just off on a side tangent with it. But here's one question I don't know. So if you have a pancake coil, let's get a picture of that. With the pancake coil, you're going to have your, you know, say north field going up here and then the south field going there. And none of that north and south will be interacting with this. It'll just be what's coming off the sides here from wire to wire. Now, if you have one like this, you're going to have, say this thing is fully charged. There's going to be the block schwall or whatever the hell it's called in the middle there. There's going to be a north down here and a south there. And so what I wonder, and I kind of think, is that that north affects all of those and the south affects all of these. And so that would mean that this setup is worse than the flat Tesla pancake coil setup for purposes of Q. But I'm not positive about that because, you know, I mean, I think about it as like the current's coming in here and then it travels around with like a current wave, and so maybe it's the same thing where it's just interacting with the ones near it. But I suppose like once the current's flowing, it's established that whole field. That's probably what it is. And then that field interacts through the length of the coil, where with the flat spiral it avoids all that. So you would say, all right, a flat spiral coil is the way to go. Now what I've been doing, I wound one of these, as I said, And then I got off on a tangent. But the next thing, and I'll really try and wrap this up, is how do you do the spacing? And I was thinking initially about, well, you know, I'll 3D print something and there'll be like a little spacer here and then a spacer there and then a spacer there. And the more I thought about it, the more difficult it became, not so much for this, but for this setup. And I had shown in a previous video the picture of Nikola Tesla next to his like giant 8-foot pancake coil, and you know, it looked like the thing was a bear to put together. And, you know, he was very good at engineering, and not so good. So it's sort of, how do you do that? And then I was thinking some more. Well, you know, the easiest sort of way to space it and have a spacer that's going to be equal to the diameter is just put a second coil in, you know, a second wire in. In other words, a bifilar coil. And you could have that second wire not do anything. And as long as it's not hooked up to any load or anything like that, all it's doing is providing a space. But once it was in place, then you start thinking about, well, what else can you do with it? You know, can you draw power off from it? How might you want to hook up both of the wires? And there's actually 4 ways to do that. We'll do a video on that. And one of them Tesla patented is Tesla counterwound pancake coil. So I made a bifilar like this, and originally I was just interested in the question of, is this going to be lower Q than a bifilar setup like that? But I saw enough here that I'm kind of going to continue to look at that. But really, just to wrap this up, so the problem with this is it's hard to wind. The problem with this is that these layers are going to interact because you're going to have the north and the south. So it's kind of, the way to maybe get nearly the best of both worlds would be a cone-shaped coil. And now you might have a little bit of interaction between one or the other, but by the time it gets to here, this one's not going to be interacting with that. So it's going to be nearly as good as your flat spiral, and it's going to be just way easier to wind. I mean, I was thinking I could print something like this and then like print a little spacer that's the diameter of the wire, and you got to thread it into there. I think it's just harder to wind that. I think it would take about 5 times as long. Whereas if I just make it a little bit of a cone, then just zip, 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 and you're done. Then I was thinking, well, instead of a cone, I should like make it a pyramid. It's pyramid power, I'm telling you. It's sacred geometry. But I decided not to. But you could make it a pyramid. Who knows? Maybe it'd like start floating around the room or something. But this is enough for now. And I'll just show you real quick with the cell phone what I've been looking at, and then end this video, and we'll do more stuff soon. What I've been diddling with on the 3D printer is just some test pieces where I want to make a cone-shaped coil where you're going to get nearly all the benefits of a flat, perfectly flat pancake coil, but it's going to be a lot easier to wind to just let the wires rest on top of each other. And I was, seeing how flat could I get it, because eventually, it's just an overhang. It's, it's like trying to 3D print a T, and you go out there and you're like Wile E. Coyote over the cliff, and it just boom. So this one, yeah, it did all right. It was trying. And this one, it's you can get away with it. But this one's fine. I was surprised. This one was a lot more narrow. And so I was going to call these, and I think I still will when I get them. I'll call them dunce cap coils. But this is 2 inch by 2 inch. This is 2 inch by 1 inch. and here's 4" by 2". The next one where I actually wind something will be 8" by 4". And this print's really clean. It's going to be really easy to wind. And this will be, I would say, because it's not done yet, but everything tells me, the 8-ball tells me, this will be a very high Q when I wind the coil. But before I even got to that, I went ahead and wound this coil, which is a single layer coil, and it's bifilar. And, you know, I'm not going to say it was a mistake, but what happened is I started getting all involved with looking at all the different kind of arrangements and the behavior that you get with with bifilar. And I will say, when you set it up counterwound, I've been seeing some interesting stuff. It's interesting enough that while I'm going to continue with Project Q, and this was the original point, was to have this and then to have a cone shape and say, hey, the cone shape is higher Q than this. And that's because these are interacting, whereas here, you know, they're not going to interact up and down. Once, you know, if it was a flat pancake, it would be perfect. But here, once you get one layer to the next, it's not going to be interacting with the layers in there. This is actually interesting enough. I printed, if you can see it, I printed, that's going to be the next one of these, which is the biggest print I could put on there. It's this big garbage can, 8" diameter, 8" tall, and I want to get some induction, and I want to see what the heck is going on, because I don't know. And that's the best place to leave that. But if it is interesting, I'll try to touch on it. If it remains as interesting as it has been with this one, I'll try to touch on it going forward. All right, I think we've covered it for now. I'll try to get videos out more frequently and make them shorter, but I'm having a lot of fun with all this, and I appreciate the comments and the kind words that people have offered in some of the comments, and also the education that people have often given me in the comments. Thank you. Stay healthy. Talk to you again soon. Bye.